Okay, well, good to see you all. Actually, as we begin, I want to point out to the people who are watching on video that there are open seats in the room. As I look around, I see probably 30 free seats in the room. I don't know if that's a good sign or a bad sign, but it was recently the ad drop date, and we did lose some of the more, students who are not as committed to machine learning as those of you who are still here. And so as a result, we freed up at least 25 seats. So if you're watching on video, I told you at the first lecture that I would let you know when there were open seats. So this seems to be the time in the semester when that's the case. So come join us if you can. Okay, so today we are going to actually do several things, but the two most important are finish our treatment of naive Bayes. We'll expand it to the case where we have continuous variables. And second, we will learn about logistic regression, which is really one of the other most widely used machine learning algorithms in practice. And interestingly, it turns out the logistic regression is also very closely related to deep networks, which we're going to start in on next week. So that's the plan for today. I have to say, I really hope that you are reading the required versions of the reading, because it will help you a lot, especially with today's material. Okay, so picking up, we already talked about naive Bayes. We talked about it being based on this formula, which is nothing more than Bayes' rule with this now familiar conditional independence assumption that we can model the probability of x1 through xn given y, which is what this term should be, as assuming that the x sub i's are all conditionally independent given the y, and therefore we can just multiply together the individual p of xi's given y. So that's the standard naive Bayes assumption. And where I want to start today is, even though we talked about naive Bayes, we assumed so far that all the x sub i's would be discrete valued. Actually, we assumed they would be Boolean valued, that xi could just be 0 or 1. And then we worked out exactly how we would estimate those probability terms of p of xi given y under the assumption that the x's were just Boolean, 0 or 1. But today, we're going to look at, well, what happens if they're real valued? And that's, of course, very common in real data. And so we want to cover that case. The standard way of covering it is to model real valued variables with a Gaussian distribution. So we'll still use exactly the same approach as we did when our x sub i's were Boolean valued. But now instead of estimating those probability terms by a maximum likelihood or a MAP estimate of how often xi would be 1 or 0, now we're going to estimate these as a Gaussian distribution. Okay, and many of you have seen Gaussian distributions before. They look like this. So here on this axis is really x, and x can vary. Actually, if it's a real valued variable, it can vary from minus infinity to plus infinity. And here's a Gaussian distribution. It's of, here's the functional form for the Gaussian distribution, sometimes called a normal distribution. Those are synonyms. And it looks kind of complicated, but here's a plot of the value of that Gaussian distribution, that is the probability density for x on the vertical axis as a function of x. And so you see what the Gaussian distribution does is it assigns a probability distribution. It's kind of a bell-shaped curve. It's the maximum probability is, if you look at this formula, actually the maximum probability is when x equals mu. So it's max when x equals mu. Mu is the mean of the distribution. And the width of this bell curve, so it's maximum when x equals mu, and so the Gaussian distribution is actually a function of two parameters, mu and theta. So so it depends on both mu, the mean, and theta. And mu determines where it's maximized, where the top of that bell curve is, and sigma determines the width of the bell curve, how squeezed or spread out it is. And so if you haven't seen that formula before, you can just kind of look at it and do some quick calculations of your own to kind of develop your intuition. Okay? And so it turns out that the mean value, the expected value of x, that is, if we want to know the expected value of x, that is, the integral from minus of infinity to plus infinity of x times its probability, that's just mu, the same place where the peak is. And the variance of x, which is, we did define variance before, and you had it on homework 1. But I'll just remind you that the expected value of x is just the integral from minus infinity to plus infinity of x times px dx. This is the expected value of x. It's just the probability weighted average value. And then the variance, of course, is this more complicated. The variance of x is actually the expected value of x minus its expected value squared. Okay, and these are just basic formulas from statistics, which were on homework 1, so I think you know those. Okay, so it's just a distribution that assigns probability to x according to a bell-shaped curve. Okay, so now how do we use this to develop our Gaussian naive Bayes classifier? Well, if these are the terms we need, remember we used to calculate these assuming x sub I was either 0 or 1. But now if it can be real valued, we're going to just say, well, the probability of x sub I given y is follows the Gaussian. And because we want this to depend on, of course, the value that y does take on, if y takes on its kth possible value, then this ought to be a different Gaussian than if y takes on its some other value. And so what we're going to do is we're going to have our Gaussian depend on what y sub k is. And so for that reason, we're now going to define for each x sub I, which is continuous valued, a different Gaussian distribution for each discrete value that y can take on. And so that's why I've given a subscript of I and k here to both sigma and mu. Okay? So it's just a way of saying for each possible x sub I and for each possible discrete value of y, we're going to have to estimate the mean and the variance that define the Gaussian distribution for that pair of y value and feature I. In practice, it turns out that if we have a lot of data, this works just fine. If we're a little bit short on data, then often we will have more difficulty estimating these sigmas from the data. And so sometimes we will assume that sigma is the same regardless of the value that y takes on. That is, regardless of k. We'll just say each x sub I feature has a sigma. And for example, that might make sense if, well, one domain we've applied this to is decoding brain image data. And there, we have a brain image, which is a 20,000 voxel image of brain activity. Those are our x sub 1 through x sub 20,000. And we can train a classifier, for example, to decide whether you're thinking about apple pie or machine learning. And so those could be the values that y could take on. And so then we would have to estimate for each of these 20,000 locations in your brain, given that we have a real valued activity that we're observing, we'd have to estimate a different Gaussian distribution conditioned on y. And that's a case where the data is sparse enough, it's expensive to collect brain image data. So we often, in that case, just simplify our problem of estimating the sigmas by assuming that regardless of whether you're thinking about apple pie or machine learning, it's going to be the same variance. And that makes sense partly because most of the noise in the data that we have for fMRI is from the instrument. That's our brain imaging method. And so that instrument inserts the noise for us, whether you're thinking about machine learning or apple pie. And so the width of the distribution that characterizes the brain activity we'll observe, that width is really dominated by the instrument noise, and it's really not influenced very much by whether you're thinking about machine learning or apple pie. And so for that reason, this is a reasonable thing to do. Okay, but that's kind of a detail. The important thing here is just we're going to use Gaussian distribution. That's it's the most common distribution that people use for continuous variables. Yes, question up here?
Naive Bayes, we assume that xi and xj are conditionally independent given line. Is there a similar analogy when we are looking at Gaussian line?
You're asking if what's independent?
In naive Bayes, we assume that xi and xj are independent given
Given
line.
y?
Is there a similar analogy that we can look at when we are looking at Gaussian line?
It's exactly the same assumption. So that's what we're doing here. The fact that we're representing that we have this product here, which we're assuming is actually the way that we can code that. So Bayes' rule tells us that this has to be here. By making the conditional independence assumption, we can rewrite this as that. So it's exactly the same conditional independence assumption. The only difference is really how are we going to now represent each of these terms? And our answer, if x is continuous, is, well, we can't just we could pretend it's Boolean, but a much more reasonable approach is come up with some probability distribution that's good for continuous x sub i's. And Gaussian is a good one. Okay, so let's see what that looks like then. Here's the naive Bayes algorithm. It looks just like the naive Bayes algorithm from before, except, whereas before we were estimating this theta parameter, which told us the probability that x would be 1 or 0, now we have to estimate the mean and the variance, mu and sigma, of the Gaussians. So during the training period, for each value that y can take on, say 0 or 1, y is still discrete. We now have to estimate, well, we have to estimate the prior that y will take on its value, just as we did when we had to estimate for, when we predicted who would live in Squirrel Hill, we had to get the prior probability that y would be 0 or 1, that you would live in Squirrel Hill or not. But now for each x sub I, when we estimate this, which we had to do in the Squirrel Hill example, now we're going to estimate it by getting the mean value of x conditioned on y being yk and the variance of x conditioned on y being yk. So basically we just, instead of estimating our old friend theta, now we estimate the mean and the variance for the continuous x sub I. And now when we go to classify a new example, it's exactly the same equation we used before. It's just that now when we want to evaluate a new example, we have our prior, which we estimated, and I called that pi sub k here. That's the parameter estimate for this. And then now we have a normal or a Gaussian distribution that takes the newly observed x sub I and its learned mean and variance and gives us the probability density for that. Okay? Yes?
Is it reasonable to say that for a Gaussian naive Bayes we would need more data, more training data as compared to a naive Bayes?
Because
we are going to estimate mu and sigma given y, right? So we need to have considerable number of examples to estimate.
Yeah. So the question is a good one. It's the question was, is it reasonable to assume we'll need more training data than we did in the Boolean case, because now we have to estimate a mu and a sigma for each x sub I. Before we only had to estimate one parameter. The answer is that for estimating mu, it's really not really a problem. It takes about the same amount of data to get a reliable estimate of mu. But for sigma, it's actually harder, because the formula for sigma depends on your estimate of mu. And so if your estimate of mu is off a little bit, then your estimate of sigma is going to be off even more. So it turns out the rate, if you were to plot how reliable is my estimate of mu and sigma, two curves, versus the amount of data that we have, or how quickly they converge to the correct estimates, it turns out mu and our old friend alpha converge at about the same rate, but sigma is slower to converge because it depends on mu. So that's a good observation. Okay, so there's the training and testing algorithm. Recall that when we had our Boolean valued x sub i's, let's suppose we have suppose x is x1 up through xn, let's say. So you have n features. Like in the Squirrel Hill example, I think n was 3. We had 3 features from which we were predicting y. In the case where x sub I was Boolean, we saw that the number of parameters that we had to estimate was how many? It was 7 in the case of Squirrel Hill, right? Which is one parameter for getting pi sub k, for getting the priors. And then for each of our x sub i's, we had to estimate 2 parameters. The probability that x sub I would be 1 given that y was 0, and also, because they don't add to 1, the probability that x equals 1 given that y equals 1. So the number of parameters we needed was 1, whoops. Was 1 plus 2n, right? 1 for the prior, and then 2 for each of our features. Now, in the case where it's continuous and we do Gaussian naive Bayes, what's the number? Well, how many do we need for the prior? Same as before, just 1. So the answer is 1 plus something. And then how many do we need for each x sub I? Suppose I just have a single x sub I. It's x sub 1. All right, I hear 2s and 4s. How many think 2? How many think 4? A lot of people are abstaining on this. Okay, it's a tie vote between the 2s and the 4s, so let's work it out. If I just have one x sub I, it's x sub 1, then I need the mean of that when y equals, and suppose y is just 0 or 1. I need the mean for x sub 1 when y equals 0, and I need the mean for x sub 1 when y equals the other value. Because those don't add to 1 either, right? And then I need also the variance, the sigma, for each of my x sub i's. So for each x sub I need 2 means, one for y equals 0, one for y equals 1, and I need 2 variances. So I need 4 for each. Jeez. 4. Okay, so there are more parameters, as one of you already pointed out. It's very important, by the way, we've talked about it several times, but you should get it in your head. What are the things that do sum to 1 and what are the things that don't sum to 1? It'll be a perfect midterm question to ask. I could give you, I could say, which of the following things sum to 1? And I could give you p of x equals 1, given y equals 1. I could give you equals 0, given y equals 1. I could give you equals 1, given y equals 0. I could give you 0, given y equals 0. And just ask you, which of those sum to 1? It would be a perfect midterm question. Okay. I think of most of my midterm questions during lecture. I don't know why that is. Okay. So now if we want to estimate those, how do we do that? It's actually pretty easy. It turns out that the maximum likelihood estimate, remember maximum likelihood? That is, what if we want, let's say, the estimate for mu and for sigma to obey the maximum likelihood principle? That is, we want the value of mu, let's say, the mean, which makes the observed data most probable. Well, it turns out the answer is we just take the mean of the sample of data. So, for example, in the case of brain imaging, where the mental state could be you're thinking about machine learning or you're thinking about apple pie, then what we need, of course, are those 4 parameters we just said. We need a mean and a variance for each of the locations in our head. And our estimate of mu should literally be for the kth y value and the ith feature, we simply calculate the average of the training examples that have that property. Here I'm using a notation which we'll use a little bit more this semester, delta function, which I just defined to be 1, and 1 if this is the case and 0 otherwise. Right? So basically whatever its argument is, it's 1 if that argument is true and it's 0 otherwise. So delta is 1 or 0 depending on whether the jth, here. Wait a minute, what's jth? Oh, jth training example, thank you. Jth, the superscript is the training example. So I just sum over the training examples. The jth training example will have some value of x for I, and I'll sum that in if y equals yk, and otherwise I'll ignore it because it's not relevant to predicting this particular mean. So this is just a way of saying take the average, sum up all the examples for which y equals yk, sum up their x values and divide by the number of them. And similarly, the maximum likelihood estimate for sigma squared is the average of how far x is from that estimated mean. Okay? Okay, and again, if you've had a core course in statistics, you know about means and variances, and these are just the standard maximum likelihood estimates for those. Okay, so now let's look at that's all there is. That's all there is to the naive Bayes. You already know naive Bayes, so the only thing we really had to talk about here was how do we handle continuous exabytes instead of discrete. Everything else just carries over. Okay, so let's look at this in practice. We have used this a lot for decoding which kind of stimulus a brain is observing when that brain is inside a fMRI scanner or a magnetoencephalography scanner, more recently. It's very straightforward. All we have to do is say, well, if we want to train a classifier to decode your mental state, then X is the mental state, Y is the label of the mental state, and the mental state itself is revealed just by all of the different intensities of neural activity observed in the fMRI scanner. Here's a picture. It looks like 4 different brains, but actually fMRI gets a 3-dimensional picture of your brain. So each of these is actually a different slice of the same brain. And there are 21 slices altogether in our images, so I'm only showing you 4 of those slices, but this is what the data looks like. By the way, the top of the picture is the back of the head, and this part is the front of the head. That's a detail. And then the color here in the picture tells how active the neural activity is in that part of the brain. So in some sense, decoding the mental state from observed brain activity is just an image classification problem. And what I've actually plotted here is not really just one image, but the plot of the muse that define what all those xi values will look like. Each different location in the brain is a different xi, given that the person's reading the word bottle. Okay? So that's what the learned classifier looks like. I'm not showing you the sigmas, but... And you see it's blotchy. Whenever I go to a cocktail party and start talking about this, inevitably somebody says, you know, you only use 5% of your brain. And then I say, it's it's almost true, but it's a different 5% depending on exactly what you're thinking about. And here you see it actually. You see the red blotches are the 5% of the brain that are really active when you're thinking about bottle. And it's a different set of red blotches if I get you to do something else. Okay, but that's... okay, so that's all there is to applying this. It's just like our old friend naive Bayes, but now because we have continuous values for the image pixels, voxels, because they're three-dimensional, we call them voxels. And then it turns out this works fine. Here's the classification accuracy for 11 different people, participants who participated in the study. And this shows the accuracy over a separate test set, separate from the training set, of decoding whether they were thinking about a word that is describing a tool, like a hammer or a screwdriver, versus a word describing a building, like tower or palace or house. And you see that we actually get, especially for people who stay very still in the scanner, we get very good accuracy. People who wiggle a lot give us still better than chance, but not perfect. Okay, so this is a real effective algorithm. It works at scale. We have 20,000 features. And furthermore, once you're done, what's interesting is we can now look at those learned X sub I distributions, and we can ask, actually here we can ask where is the activity in your brain that distinguishes whether you're thinking about tools or buildings. In fact, here's an even easier thing. In this case, what we did was we just built a classifier based only on 27 voxels. It's like a Rubik's Cube, 3 by 3 by 3 voxels, which is about a centimeter cubed of brain tissue. And we trained a different classifier using this cubic centimeter of brain tissue versus that one. We trained one for every Rubik's Cube that we could move around inside this 20,000 voxel brain. And what you see plotted here is actually the accuracy at distinguishing, in this case, buildings versus tools. And you can see there are distinct regions in the brain where you get high accuracy by looking just at the neural activity in that region of the brain to distinguish, in this case, whether you're reading a word about tools or a word about buildings. It's even more interesting, but I shouldn't go into the details. I'll just point out this spot in your brain is actually a region called premotor cortex, and it's part of your brain that's active if you're thinking about doing this or any kind of physical motion. And it turns out, even though you're supposed to lie very still in the scanner, and people do, if I get you to think about hammer, I just did, it activates neural activity in premotor cortex, even though you're not actually moving your arm, but it's the same region of your brain that would be active if you were planning to move your arm. So it leads to very interesting neuroscience results about neural activities that represent meaning are grounded in sensory motor regions of the brain. Okay, but that's not our topic for today. And I'm instead of getting launched off onto that, I'm just going to move along. Okay, so the point of that was you now know about Gaussian naive Bayes. It's actually quite straightforward because you already knew about naive Bayes. We just substitute a Gaussian distribution for our old Bernoulli distribution. And we can use maximum likelihood estimates. If we prefer, we could use map estimates to estimate the parameters, and then we classify our examples. And it's a very popular algorithm for dealing with continuous valued variables. In fact, let me ask you a question. Suppose I had a classification problem where some of my variables were continuous valued and others were Boolean valued. some of my x sub i's are brain image pixels, and other x sub i's are you taking the machine learning course? And what's your gender? So those are two Boolean valued. How would you design an algorithm that would use a mixture of continuous and discrete valued x sub i's? Yes?
Take the classifiers and then weight them?
Okay, so one possibility is train two different classifiers, one on the continuous variables, one on the discrete ones, and then let them vote in some way. I guess that's, yes?
Can we make the discrete ones continuous?
Yeah. So we could just build one classifier. Remember, the whole definition of naive Bayes is just this. And so what we can do is, for the x sub i's that happen to be continuous, we'll model that with a Gaussian distribution. For those other x sub i's that happen to be discrete, say Boolean, we'll model those just by estimating theta the way we already knew. And because we assume they're all conditionally independent, we just then multiply together all those probabilities. It's a perfectly reasonable thing to do. See, so if you really, now you're starting to see what we're trying to do in this course is actually give you a set of principles that are illustrated by specific algorithms, but then give you the ability to boutique design your own algorithm by going back to basic principles and just thinking through with common sense in most cases how you would deal with this other kind of data set that has these slightly other characteristics. Some of the principles that we've talked about that are relevant to that so far are continuous and discrete x sub i's, and also maximum likelihood estimates and map estimates, which are very important principles for helping to deal with, for example, overfitting or taking advantage of prior knowledge. And we'll have some more principles coming. Okay, so let's end there on Gaussian naive Bayes. I think here's what's important. You should know about conditional independence. That underlies the whole idea. That's the naive in naive Bayes, is the conditional independence assumption. Its consequences, and remember when we introduced it, we were training a whole joint distribution on P of, the whole joint distribution correctly versus making this conditional independence assumption and seeing that if we did, it would dramatically reduce the number of parameters we had to estimate. And then how you would actually train them and use them. Okay, so now what I want to do is move on to a different algorithm. Actually, before we do, are there any sort of last questions or comments? Yes?
Why didn't we see if we can do map estimate for the mean and the variance for Gaussian naive Bayes for languages?
Right, so the question is, did we not cover how to do a map estimate for Gaussian naive Bayes? You're correct. Good observation. We did not cover that. If we did, it would turn out, for example, that in a map estimate for mu, we could talk about the conjugate prior, and it will turn out to be the same principle as what we saw before, which is that a map estimate for a Gaussian involves effectively putting in a prior that is equivalent to hallucinating x sub I values. So just like our prior on estimating theta for a discrete value, and we used the Dirichlet prior on that, that corresponded to introducing imaginary data where things turned up x equals 1 or 0. It turns out that in the map estimate for the mean of a Gaussian, for example, it corresponds exactly to also introducing imaginary examples that indicate our prior assumption about the mean and the variance of the x's that we'll observe for a particular y. The mathematics are a little messier than they were in the other case, which is why I didn't do it. But the principle remains actually the same. Okay? All right, then let's move on to one of my favorite algorithms. It's in my top 5. Logistic regression. The reason I love logistic regression is it asks the question which is the elephant in the room. Like, nobody asked me this before, but any time during the last 2.5 lectures, somebody could have raised their hand and said, why are we going through Bayes' rule? We're trying to get P of y given x, and you're forcing us instead into this naive Bayes algorithm that instead predicts x's given y. Why don't we just directly learn P of y given x? And that's the question that logistic regression would ask if it was an agent. But it answers, because the whole idea of logistic regression is don't even bother. If what you're interested in is P of y given x, don't even bother with Bayes' rule. Just estimate P of y given x. So let's say a little bit more about that. So again, suppose we're interested in learning some function from x to y, or we could say equivalently, we're interested in P of y given x, same thing. Now, we just talked about Gaussian naive Bayes, which is set up the following way. X is a vector of real valued features in Gaussian naive Bayes. Y is a Boolean valued thing, let's say. It's at least discrete valued. Let's consider the simpler case where it just has 2 possible y values. We assume in Gaussian naive Bayes that all the x sub i's are conditionally independent given y. And in the bottom line, we model P of y as simply a Bernoulli distribution. That is, we only have to estimate one parameter to tell us what's the prior that y equals 1. And then this is one of the ways. For a Gaussian naive Bayes, we're going to model P of x sub I given a particular value of y as a Gaussian distribution. And here, I'll just point out, I'm making this assumption that sigma depends on I, which x sub I we're talking about. But I'll assume here that sigma doesn't depend on which y we're talking about. Which again would be a reasonable assumption, for instance, in the brain imaging scenario, where, as I mentioned, most of the variance in the data we observe is due to noise of the fMRI scanner. And the fMRI scanner doesn't know or care whether you're thinking about tools or buildings or apple pie and machine learning. It's just going to give you the same noise distribution. So, but I am going to make these assumptions. So this is basically the Gaussian naive Bayes assumption. Where I assume sigma just depends on the x sub i's. Now I can ask, what does that imply about the form of y given x? And it turns out, we'll see on the next slide, it implies that P of y given x has a particular functional form. And once we know what that form is, we can see what the parameters in that functional form are, and then just directly estimate those. And that's the whole idea of logistic regression. Let me say it again. First step is, let's make some assumptions which are basically a variant of Gaussian naive Bayes, and ask if this is how we're going to model the probabilistic scenario that we're dealing with, then what is going to be, what is that going to imply is the functional form of y given x. And then logistic regression is simply an algorithm that uses that functional form and directly estimates the parameters from the data. Okay, so let's see. Oh, here it is. Here's the answer. It turns out what it implies is that P of y given x is of this form. So in particular, just to be more precise, the probability that y will take on the value 1 instead of the value 0, given a set of real valued features that we model as following a Gaussian with sigma sum i's, is going to be this form, where the W0 and the WI's actually can be calculated directly from the mu's and the sigmas that we trained in our naive Bayes classifier, except that when we train it with logistic regression, instead of estimating the mu's and the sigmas and then calculating these, we're just going to directly estimate these parameters. So it's really kind of a remarkable thing. So let's look at why that's true. And here, this is spelled out in detail in the reading that I want you to read for this lecture. So I'm not going to go through it, except here is the whole derivation in a page. So let's see what it is. So again, what I'm claiming that this is the functional form of P of y equals 1 given x. And
Can you repeat how you calculate W0 and W1?
we haven't described how we're going to calculate W0 and 1 yet, but we will. So I'm going to just start with my usual Bayes rule, which is here, right? The probability of y equals 1 given x is just Bayes rule. And then in this first step, all I do is divide every term by the numerator up there. Divide every term by this quantity. So now, of course, in the numerator, now I have a 1, and then in the denominator, I have a 1 plus that right-hand side, that right-hand denominator term divided by the thing. And then in this step, it looks silly, but it's going to end up being helpful. In this step, I do nothing except put in the log function and then take the e to that natural log, which is basically identity, right? E to the log of x equals x. So I'm just substituting that because now in the next step, what I'm going to do is separate out the product of the log into the sum of the logs, or sorry, the log of the product into the sum of the logs. And so here is this term. And this one is just the log of the probability that y equals 0 over y equals 1. And recall I use pi as my parameter for that prior P of y equals 1. And so now the beautiful thing is this step ends up here again. To remind you is the definition of the Gaussian distribution. So the ratio of two Gaussians for y equals 1 and y equals 0 ends up turning into this form. So if you work it out, you take the log of this ratio, and again, we are assuming that sigma depends only on xi and not on yk. But if we make that assumption, then it turns out this equals this. So it's the sum over I of the logs of those, but those are just this. And it takes some arithmetic to get from here to there. I encourage you again to go through the reading to get that. I'm not going to go through the arithmetic here. But the bottom line is, this is now the form of P of y equals 1 given x. It's 1 over 1 plus something exponentiated, and that something is a constant independent of x sub I, plus this sum, which has a bunch of other constants independent of x sub I, of the value of x sub I, plus this term, which is another constant, times x sub I. So, for example, this term is the wi from here. And the w0 is just the sum of all those other constants. W0 is the sum of this constant plus sum over I of all those constants. Okay? So there's the simple derivation of what is the functional form of y equals 1 given x. It is indeed 1 over 1 plus exponential of some linear sum of, weighted linear sum of the features of x. Okay, so now who cares? I care, and you will too once you see how cool this is. This is very cool because now that we know that P of y equals 1 given x is of that form, what does that imply? Well, how do we get y equals 0? 1 minus that, right? So that's easy. That's just going to be x of w0 plus sigma I wi xi over the same denominator we had before. And if you don't believe me, just add those two things together and you get 1. Okay? Now, what does that imply about the ratio of P of y equals 0 to y equals 1 given x? Yeah, the denominators cancel out. So this is now just exp of this. And what does that imply about the log of that? Even better. And why do I care about this? Well, if this is my decision surface, is I'm going to look at whether this is more or less than 1, right? If this ratio is more than 1, then I'm going to say y equals 0. If the ratio is less than 1, I'm going to say y equals 1. And similarly, I'm going to look at whether this quantity, the log of that, is greater than or equal to 0. So now, we know not only the functional form of P of y equals 1 given x, but we know that the decision surface, our final decision of whether to label x a positive or a negative, y equals 1 or y equals 0 label, is going to be a linear decision surface on the continuous values of x sub I. Although the probability will, of course, follow that form, but if we just look at which probability is greater, then that's going to give us a linear separator in the Euclidean space that x lives in. Okay? All right, so I was so excited. All right, so what does that function look like? It looks like this. So here, if we take 1 over 1 plus exponential of minus b, and I vary b from minus infinity to plus infinity, here's the middle of it. You can see, well, if b equals 0, then I get 1 over 1 plus e to the 0. That's 1/2. If b gets bigger, then I have 1 over 1 plus something that's e to the minus something. And as it approaches infinity, that becomes e to the minus infinity, which is like 0. So then I end up with 1 over 1 asymptotically. And over here I end up with 0. This is called the sigmoid function. 1 over 1 plus exponential of minus x is called the sigmoid function of x. And so we can think of our probability that we're estimating as first computing some linear function of x and then feeding it into this sigmoid function to get a continuous probability. And remember when we said we're interested in the case, our decision surface will be just in the case where the probability that x equals 1 equals the probability, that y equals 1 given x equals 0.5. So that'll be right here, where this linear function is 0. That'll give us a probability of 0.5 that y equals 1. Okay. The sigmoid function turns out to be at the heart of neural network algorithms because many neural networks are built out of many different units, each of which has exactly this sigmoid of a linear function of x form. So many standard neural networks are actually just built out of many units, each of which has exactly this functional form. But for us, we'll get to that. But for this lecture, we're just interested in looking at it this way. But I had to tell you about the neural net connection because I know many people are interested in that kind of connection. All right, so now we can also generalize this in a very straightforward way to the case where y can take on more than 2 possible values. And similarly, if you think about it, you can generalize naive Bayes also simply to the case where y can take on multiple discrete values. Still should be discrete, not continuous y. But for example, suppose I have y could be 3-valued. Back to my brain imaging experiment, y might be, are you thinking about tools or buildings or lunch? So there could be three values for y. And in this case, what happens is it turns out that if y takes on r possible values, then for each of those, except the last one, we learn a separate set of weights for our linear combination of the x sub I features. So for y taking on its kth value, I need to have a weight associated with that kth value. And I need that for all of the possible r values except for 1, because given x, the sum of all these y equals 0 given x plus y equals 1 given x plus y equals 2 given x have to add up to 1. Y has to have some value. So we can just say that the final one is 1 over that same denominator. And then again, just like before, you can prove these add up to 1 just by summing them all and seeing that it is. Okay, so it's easy to generalize this to the case where y has many values. And now that you see this, I'm sure you could answer a midterm question that asked you how you would generalize naive Bayes to 3 values for y. So it'll be just as straightforward, as long as you're not feeling pressure. Okay, so now how do we train this? How do we estimate those parameters, those W0, W1, W2, all those things? Well, we only know 2 things. We know how to do maximum likelihood estimates, how to derive those. We know how to do map estimates. And so if we wanted to get a maximum likelihood estimate, then we would want to pick the vector of parameters. I'm using uppercase W there to mean the whole collection, the whole vector, W0, W1, W2, all those parameters. The maximum likelihood estimate for that collection of parameters would be the vector of parameters that makes my training examples most probable. Just like our maximum likelihood estimate for theta for the coin was picking the theta that makes the observed coin flips most probable. And here again, the superscript means the ith training example. So x1, y1 are the observed first training example. xl, yl are the observed last training example, and everything in between. And if we assume those training examples are independent, identically distributed, just like we assume the coin flips were independent, identically distributed, that would give us this. So we want the W that maximizes just the probability of each training example, and we multiply all those probabilities together over the whole set of training examples. But now actually when we train logistic regression, we do something a little bit different. Instead, we go for the maximum conditional likelihood estimate. That is, what we're really interested in the end, is P of y given x. So we can make up something we call the maximum conditional likelihood estimate, which is we want the W, which is the argmax of, again, the product over all of our training examples. But now I'm going to ask for this instead. I want the most probable y given the observed x and my W. So this is a little different from this. This is making the whole training example dependent on W. But actually, in logistic regression, what we just derived was a formula for P of y given x. And so if we really wanted this, we'd have to add some more parameters that captured the P of x. It's like the denominator in Bayes' rule, which we always try to get away from. And so instead, it's fine to just say what we really want is over the L training examples, we just want the parameters that make the observed label for each of those training examples as probable as possible, given that we know the x. We don't have to worry about how probable x is. It's just the example we got. What we're really interested in is picking W's that'll maximize the probability of the observed y given x. And so this is called the conditional, for obvious reasons, conditioned on the observed x's, conditional likelihood estimate. And this is the quantity that we actually optimize when we train logistic regression to estimate directly from the training data the W's. Okay, now again, I'm going to go quickly through this and count on you to read the reading. But basically the idea is if we want the maximum conditional likelihood estimate, we're assuming this is the form for P of y equals 0 or 1 conditioned on x and the weights. We get this, and the way this is the part I'm going to go over quickly. If we ask, what is the log of that conditional likelihood? As before, it's going to be convenient to work with logs, just because it makes the arithmetic easy. But if our conditional likelihood, we take the log of it, now we have the log of the product over all of our L training examples of the probability of y given x. Then that turns into this form. And I guess one way you can see this is in the case where y can only be 0 or 1, this form is really an if statement. If y equals 1, we're going to use this term, and this term will be zeroed out. If y equals 0, this term will be zeroed out, and we'll end up using this one. So this is, again, just our way of writing an if statement as arithmetic. So basically, we're going to sum over all of our examples, and for the cases where y equals 1, we're going to have the probability that y equals 1 given x. For the cases where y equals 0, we're going to have the probability that y equals 0. And then I can manipulate this, for example, by dividing. Here it gets trickier. Here I have to multiply that out and do some manipulations to get here. But in the end, it ends up being this form. So it's the sum over our training examples, that's the L index, and the I is just the x sub I index. And so here's a form for the conditional likelihood. It's not that pretty, but it does lead to two observations. One is, it is a concave function of our parameters. That is, if we plot this function against all the possible w sub I values, there's just one nice optimum. The bad news is there's no known closed form solution for this. We can't just solve for w's given the observed values of our x sub i's and our y's. So instead we use a very general technique, which some of you probably already know, called gradient descent or gradient ascent. It doesn't really matter. And the idea is this. Suppose we have some function we're trying to optimize, and I plot the value of that function on the vertical axis. And then I have a set of weights I'm trying to adjust, like W0 and W1, on the other axes. Then for every combination of W0 and W1 that I could think of, there's some value of that function. In our case, you could think of this as, say, the negative of that thing we were trying to optimize actually looks like this. If I negate it, then it'll look like this. And so if I want to minimize the negative of the conditional log likelihood, or maximize the non-negated one, but here I'm plotting down as good, so let's say the negated likelihood, then the idea of gradient descent is very simple. It's this. Build an iterative algorithm whose job is to find the best combination of W0 and W1, or however many W's you're trying to estimate. And that algorithm works this way. First, you start out with a random choice. Suppose we start out with this choice of W0 and W1. You calculate your function for that particular set of choices of W0 and W1. We calculate the conditional likelihood. And then we calculate the gradient. The gradient is the vector. This is actually the gradient right here where I drew my circle. That's the gradient. That's the direction we want to move W0 and W1 in order to go most steeply down the surface that we're trying to minimize. And it turns out the gradient, with respect to the E as the function we're trying to minimize in this picture, the gradient is simply the derivative of that function with respect to W0 and the derivative with respect to W1 and so forth. It's this vector. And of course, this vector will have as many W's in it as there are that we're trying to optimize. In this simple picture, I only drew 2 W's, so it would be W0 and W1. That's it. But this vector of derivatives gives us exactly the vector, the direction that I've drawn the blue circle around. That's the direction that we move the weights so that we most steeply descend the surface of the function we're trying to minimize. And so the gradient descent algorithm simply says, know how to calculate the thing you're trying to optimize with respect to W, and then start with a random choice of W, W0 and W1, the vector. Calculate the gradient, calculate the direction of steepest descent, move your weights in that direction a little bit. Why a little bit? Well, because this surface, if it's not linear, the derivatives are going to be a function of where you are on this W0, W1 plane. So just move a little bit, in fact, this much. We have a parameter that tells how far a step size to take. And then, and moving the vector of weights in that direction simply means add to each individual weight the derivative of the air with respect to it. So it's a very straightforward algorithm. And you just keep going downhill until you have to be careful about the stopping condition. You want to go downhill until you think you're at the bottom. And one way to do that is to keep track of whether when you make these changes in W, you're actually still going downhill or whether you're starting to go uphill. Yes?
Professor, what if there are several different, local.
Oh, good. Excellent question. What if the surface doesn't look as beautiful as mine, but it looks more like this? Okay, now we got a problem. Because you can see you could get trapped in a valley that's not the pleasant valley. And that is a serious problem. Fortunately for us people interested today in logistic regression, we can prove that the surface is of this form. There's a single local minimum. It is the global minimum if we're trying to minimize the negative conditional likelihood. And so one of the beautiful things about logistic regression is gradient descent is guaranteed to give us the right answer. One of the difficulties with neural nets is that even though we use gradient descent there, it's not guaranteed because the surface looks more like that other one that I painted. So that's a great question. Yes?
Professor, does this algorithm take into account constraints?
This one doesn't. You can bring in additional constraints, and people sometimes do that. You can modify it to take into account constraints. For example, you might want to constrain it so, in logistic regression we don't, but suppose somebody wanted to constrain it so that the weights sum to 1. Then actually not every place on this plane of W1, W0 is legitimate. If they had to sum to 1, then there'll just be a line somewhere on that surface, which are all the legal points. And so in that case, what some people do is modify this to take a gradient step and then move your answer to the closest place from there to the line of legitimate solutions. So there are a lot of extensions to this. I want to talk about just one before we end. So there are two dominant ways of doing this. One is what I told you, and that's sometimes called batch gradient. Why? Because we're summing over all of the training examples when we calculate the conditional likelihood. We're summing over every training example. And we calculate that likelihood, we get its gradient, the derivative of that with respect to each weight, and then we take a step. We take a small step if we're careful because we don't want to miss the bottom of the hill. And then we go through that same process again. So that's called batch gradient. And it's just compute the gradient, update the vector, repeat until you're happy, until you're at the bottom of the hill. There's the second approach, which is introduced simply as a computational efficiency issue, or at least that's the dominant reason. It's called stochastic gradient descent. And what it does is instead of using the whole set of training data to compute the gradient on each step, you just randomly choose a training example out of your training examples. You compute the gradient just with respect to example D, which you chose, and you take a step. You update the parameters, and then, again, you make a choice, a random example, and choose it, and get the gradient with respect to that. Sounds really weird. You can imagine that instead of going straight down the hill, now you're going like that to get down the hill. Will you go down the hill? Well, it turns out it's easy to prove that if you make your step size small enough, then this will, as this step size approaches 0, this becomes a perfect approximation to that. Right? Think of it this way. Suppose I have 1,000 training examples, and I decide to use a learning rate of 1, step size of 1. But now instead I do this, and I use the step size of 1 over 1,000. Now each training example I look at only has 1,000th of an effect on that the whole batch gradient had. But if I sum up those 1,000 small steps, as I say in expectation, go over all 1,000 distinct examples, then as my gradient, as this rate and this approach 0, this becomes a better and better approximation to that gradient. So in practice, this stochastic gradient method is usually the one that we use in practice. And it's simply because of efficiency reasons. And that's all really there is to say at this point about stochastic gradient. Okay, so let's summarize. Let's end there. So today we saw a couple things. First, Gaussian naive Bayes. How do we deal with x sub i's that are continuous instead of discrete? Well, of course, we still have to get p of x sub I given y. It's just that now we need some probability distribution that's appropriate for continuous xi's, Gaussians. But then, logistic regression, we introduced. But remember, we started with this specific question. If we are using Gaussian naive Bayes, what does that imply about the form of p of y given x? And it implies that functional form that we came up with. And so then logistic regression is based pretty much, can be derived from the same assumptions of that variant of Gaussian naive Bayes. But it gives us a way to just express p of y given x directly. And then we can use gradient descent to estimate the W0 up through Wn's. And now, instead of having 2n plus 1 parameters, or 4n plus 1 parameters, if we have n x sub i's, I just have n parameters plus 1, my W0. Okay, so again, please read the reading. It has the details that will help you with this. See you next time.